So, all right, that's going. So starting now on Euclid. So today we're going to be talking about Euclid and focusing on mostly on Euclid's elements. The point being to see how Aristotle set the foundations for systematic bodies of knowledge, and then Euclid's work is the first systematic body of knowledge, his elements. So while Euclid's relatively unknown, it's his elements that we're mostly going to be focusing on here today, but it's good to have a little bit of Euclid as well. So before we jump straight into this, we need a little bit of historical context about where Euclid was and how Aristotle continued. So going back to the Persian Empire, right before the Greco-Persian Wars, this is roughly what the Persian Empire looked like, right? Conquered pretty much the known world, and this is pretty much as big as they were until Alexander the Great comes. They lose this in the Greco-Persian Wars and the stuff up here, but for the most part, they pretty much maintain their empire until Alexander the Great comes along. Now, the reason that's relevant for what we're talking about today is Alexander the Great was a student of Aristotle. Remember that? Aristotle grew up, came from some town up here, which is right next to Macedonia. Macedonia is up here. Alexander the Great was a Macedonian. So Aristotle had close ties to the royalty in Macedonia, and so he taught Alexander the Great, and he also taught, more importantly, a friend of Alexander the Great's by the name of Ptolemy. Ptolemy, very important name in history, Ptolemy. So Ptolemy is a close friend of Alexander the Great's. Aristotle didn't just teach Alexander the Great, he taught a bunch of upper-class youths, one of which was Alexander the Great. Another of those was by the name of Ptolemy. Alexander the Great and Ptolemy are good friends. When Alexander the Great goes and starts conquering the world, Ptolemy is one of his generals. With me so far? So Ptolemy, general of Alexander the Great's, fights with Alexander the Great, and he was also a student of Aristotle's. So Alexander the Great goes on his conquest, and here's the empire that Alexander the Great creates. I just wanted a more zoomed out map to remind you about where in the world we're talking about. So this is pretty much conquering the Persian Empire, and then it also has this stuff up here, which wasn't part of the Persian Empire, which is Greece, Macedonia, and then conquers the Persian Empire and goes a bit further east than the Persian Empire was, but here's the Mediterranean Sea, obviously, here's Greece. Still at this time, Rome's just a little nothing right there. So this is the conquest of Alexander the Great. We're talking about 323 BC. He goes and he conquers the known world. In particularly, notice that he conquers Egypt. So Egypt now comes under the rule of the Greeks. Now Alexander the Great, he dies in his early 30s, and the instant he dies, his empire just crumbles, and his generals, 4 of his major generals seize powers. They kind of split the kingdom up into 4, and each of them takes over a good chunk of the empire. The important part is Ptolemy ends up taking over this part down here, Egypt. So Egypt comes under the rule of Ptolemy, who was taught by Aristotle. And Ptolemy is an ancestor of Cleopatra. Give you a sense. So the Ptolemies rule Egypt all the way until the time of Rome. So Egypt was ruled by people, by Greeks, all that time, in bloodline. And so when Ptolemy sets up his empire down here, well, when he takes over running that empire, he is very education focused, and his line is very education focused, and they kind of follow the thinking of Aristotle. So after Aristotle's death, his works are forgot relatively quick, and they're given to some relative who doesn't really care about him, puts him in a basement. And so his works are forgotten relatively quickly in history, but his school of thought, his intellectual heirs, continuing to stay down here by the name of Alexandria. It's a city that Alexander built when he came down and conquered. It was a city that became a massive, thriving city. You might have heard about the Great Library, or the Library of Alexandria. It was located in that city, Alexandria. Or you might have heard about the Great Lighthouse, or the Lighthouse of Alexandria. It was located in that city, Alexandria. So that's the city that we're talking about. That's one of the cities that Alexander established and Ptolemy made thrive. And that is a city where Euclid goes to work. So while Euclid isn't a direct student of Aristotle's, he's viewed as one of the intellectual heirs of Aristotle's. And he follows Aristotle's way of thinking, and we'll see that in how he sets up his work. Now, what do we know about Euclid himself? Almost nothing is known of Euclid. He was born roughly 350 BC, died roughly 250 BC. Give or take a couple decades on each of those. We have no clue. We just know that he was in Alexandria during the rule of Ptolemy I, which is the Ptolemy that we've been talking about this whole time. So almost nothing is known about his life, except for that he's the one who put together the Elements. And the Elements is what we're focused on here. The Elements is the name of a 13-book collection, which basically deductively derives all the mathematics of the day. And we'll get a sense for what exactly we're talking about there by deductively derives it all. But those books are the reason that Euclid is so famous. Now, he didn't necessarily come up with all the proofs that are in those books. He might have come up with a couple, but for the most part, all he did was took all the knowledge that was known at the time, all the mathematical knowledge that was known at the time, and just organized it all into this structure. So he's going to organize it so that from 5 postulates and 5 axioms, all of geometry can be derived. So that's what he's so famous for, and what his great contribution to the world. And Euclid's Elements are absolutely a massive, were a massive contribution and very, very influential. So the Elements, it's the second most published book, series of books, there's 13 of them, but what they called a book back then isn't quite what we think of a book now, but they are heavy. So second most published book, and possibly the second book to be printed. Now when we say the second most published, that doesn't mean it has the second most copies printed. You have to republish it every so often. So throughout history, it's been published over and over and over again, meaning it's consistently been relevant. Does that make sense?
Yeah.
And second to, you can probably guess, the most published book.
The Bible.
The Bible, good guess. And it was possibly, there's some arguments that was the second book to be printed after the Bible. So Gutenberg invents the printing press. First thing they print out are Bibles. What's the next thing they print? Euclid's Elements. Is that foundational? That fundamental? Euclid's Elements, this was a standard textbook for learning mathematics from roughly 300 BC to roughly the late 1800s. You had everyone from Archimedes to Abraham Lincoln studying Euclid's Elements to learn mathematics. Quick quote, not until the 20th century, by which time its content was universally taught throughout other school textbooks, did it cease to be considered something all educated people had read. You were not considered educated for over 2,300 years, or for over 2,000 years, if you had not gone through Euclid's Elements, or at least a good portion at the start. That's how foundational and fundamental this series of this work is. So now we'll go through just the first bit of the work, just to give you a sense for what it was, how it worked, and why it was the example. Because Euclid's Elements now becomes the standard by which systematic bodies of knowledge are judged. Everyone's trying to do in their separate fields what Euclid did with mathematics. When we're trying to develop physics, we're trying to do it the way he did mathematically. Some philosopher by the name of Spinoza, he tried to develop his philosophy the exact same way Euclid developed his elements. They tried to follow this exact standard. It becomes the standard. And we didn't improve on his logical rigor until roughly 150 years ago-ish. So, stood for a long time without any improvement. Last thing to note before we break this down is of every single thing that Euclid proved in that book, so Euclid, it's just tons of proofs. Not one of those proofs was later found to be false. All that's happened is we've come up with better ways and more rigorous ways of proving the same things. There isn't a bad theorem in the work. We might take issue with the theorem saying it's not rigorous enough, he's being too fast and loose, but he never came to a false conclusion. Does that make sense?
Yeah.
It's absurdly impressive. Okay, so now we'll go through the 4 types of things that we'll find in the books. So at the start of each of the 13 books, Euclid starts out by listing the definitions of the words that he's going to use in that book. You all have a pretty good idea for what a definition is, right? Okay. Now, this is one of the places where he's criticized, Euclid's criticized, in our more rigorous logic now, because he tries to define all the words he's going to use. And technically, you can't do that. Imagine for a second that I gave you, let's say you don't know a single word of French, and I gave you a French dictionary. And I said, there you go, now you know every word of French. Because anytime you need to know a French word, you can just look it up in the dictionary, right? No, because every time you look it up in the dictionary, it just gives you more French words. And so you gotta go look up those French words, and it just gives you more French words. And you keep looking up, and one of two things happens. Either you find a French word that's not defined in the book, or it becomes circular, and you get back to where you started. Yeah. Neither of those work. So you need some French to be able to start using a French dictionary. You need some undefined terms. So he tries to define everything, technically invalid, but it still gives us intuition, and so we'll still be able to go along with his definitions. So that's one way that we're more critical of him now, but still amazing what he does. So at the start of each book, he'll give definitions, and then after the definitions, he'll start giving the propositions. He'll start proving things. He'll start listing out the theorems. So that's how each book starts. It gives you the definitions, and then it starts proving things, with the exception of the first book. The first book also has what we call postulates and common notions, or axioms. And these are your beginning assumptions. These are your beginning assumptions that you use to start proving with. Right? So you'll start with these beginning notions to prove your first couple theorems, and then you can start using these notions in your theorems to start proving other theorems, and it starts building and building and building on top of itself. And we'll see how that works. Now there's a difference between his postulates and his common notions or axioms. His postulates are the assumptions specific to geometry. These are the things that only have to do with geometry. His common notions or axioms, these are things that he gets from Aristotle's organon. These are the conclusions of logic. These are the things that are valid in every field of study, every science. It doesn't matter if you're talking about geometry, or if you're talking about arithmetic, or if you're talking about physics, or chemistry, or biology. These hold in every field. These are specific to just geometry. And that's why it breaks them down that way. So this is a consequence of Euclid's organon, Aristotle's organon, and then this are just the postulates specific for geometry to get geometry started. And that's the difference between those two. That make sense? Yep. Okay, so now let's actually jump into the work. And we're going to go over 23 definitions here to define all these words. Make sure you understand the words, and then we'll go over the assumptions and then do the first couple theorems, and you'll get a sense for how these books work. So, definition 1, a point is that which has no part. Now, this is one of his definitions that we would take issue with today. A point is that which has no part. What do you mean it has no part? Well, zero dimensional. What do you mean it's zero dimensional? Well, it's just a point. It's going to end up circular if you keep asking, what do you mean? Okay. So you can't really do that. How exactly you do this, that's a topic for a geometry class, but there's ways that we get around this. But it at least gives you intuition. What does he mean by a point? It's that which has no part, just a point. I just want to make sure you have good intuition for what all these words mean. We don't need to make sure you have a rigorous understanding of the words, because you have a good idea of what they are for the most part anyways. So everyone go with definition 1. Point is that which has no part. It's just a point. There's no substance to it. Good? Okay. A line is a breadthless length. Now he uses line the way that we talk about a curve. So the way that he's talking about, this is a line, and this is a line. Okay. So what is the property of a line? It's a length. These are both a length without any breadth to them, no thickness. A breadthless length is a line. When we talk about line, he really means a segment. Our language has changed a little bit since the translation of this. Good? Mm-hmm. Okay, definition 3. The ends of a line are points. Since he's always, when he talks about line, he always means a segment, then the ends of a line are points. Make sense? Yep. Okay. A straight line is a line which lies evenly with the point on itself. Now, that one's hard for you to wrap intuition about. It's historical that he describes it that way because it's actually how you would construct a straight line back in the day. So we don't need to get into that. All you need to know is what he means by a straight line is what we mean by a straight line segment. It just means this. It's straight. It doesn't curve.
Okay.
Good? Right. A surface is that which has length and breadth only. Length and breadth, no height. So it's two-dimensional. It has a length and it has a breadth. So this right here is a surface. Filled in. We typically say a width and a height. He's calling it a length and a breadth. Is that what he says?
Yeah.
Okay. Two-dimensional. That's what a surface is. Okay, the edge of a surface are lines. So take any surface you want, like a square, and he's thinking about filled in like that. The edge of it is always lines. Make sense? Okay. A plane surface is a surface which lies evenly with the straight lines on itself. Now everything I've been drawing here is a plane surface. What's a surface? That's a surface but not a plane surface. Think about a paper like this. It's still a surface, it's still just two-dimensional. Pretend that it has no thickness. So here's still a surface, but it's not a plane surface. When he's talking about a plane surface, he means it lies flat. Lies evenly with itself. Okay. A plane angle, just give you a sense for a plane angle rather than wrap your head around the definition. Plane angle is exactly what you think of by an angle. Look at that angle. That's a plane angle. Doesn't go in or out of the whiteboard at all. Not only is this a plane angle, this is a rectal linear angle. What's the difference? Notice that the lines I used were straight when I constructed this angle. If they were curved, and I said, look at this angle, plane angle, but also a rectal linear angle. We basically just use rectal linear angles. And this is pretty much what we just call an angle in math now. Okay. When a straight line standing on a straight line makes the adjacent angles equal to one another, each of them is a right angle. Okay, so when I have a line and a line, so I have two straight lines, so they end in points using Euclid's terminology. If I take this line and I take this line, and I construct it so that this angle is the same big as this angle, these two angles are called right angles. And we have a special notation for when it's a right angle. We use a little square box there instead of a rounded thing to mark the angle. Make sense? Okay. An obtuse angle is an angle bigger than a right angle. Here's an obtuse angle. And then next we'll do an acute angle is an angle which is less than a right angle. Acute angle, obtuse angle, right angle. Any questions on any of those?
Nope.
We already talked about acute angle. A boundary is that which is the extremity of anything. It's typically what we mean by the word boundary already. Again, that's just giving you intuition. A figure is that which is contained by a boundary or boundaries. So if I draw some boundaries, what's the figure? The thing contained by it.
Okay.
Everything inside that. Look at this figure. You already were thinking the right thing. Okay? A circle is a plane figure where, no point reading that, but you already have the understanding of what a circle is. So when I have a circle, well, we'll read the definition really quick. A circle is a plane figure contained by one line, that's the circumference, one line, remember his lines don't have to be straight, one line such that all the straight lines falling upon it from one point, meaning the center, among those lines within the figure equal one another. In other words, all the radiuses are equal to each other. So on a circle, the distance from the center to this point is always equal to the distance from the center to this point is always equal from the distance to center to this point. So picking a point on the extremity, draw a line segment to the center. We call that the radius of the circle, and the radius is the same no matter where you draw it. And the point at the center of a circle is called the center of the circle. We already just called it that to help you understand the definition. Good?
Yep.
Important to understand when he talks about a circle, difference in how we use language. When you talk about a circle, you just think about the points out here. You don't think about this point as lying on the circle. When he talks about circle, he's actually talking about the disk. He's thinking about this filled in.
Okay.
So well, yeah. And that's how they also talk about squares. When he talks about a square, he means a square filled in. When he talks about a rectangle, he means a rectangle filled in, not just an outer edge. Okay, next definition. A diameter of a circle is a straight line drawn through the center, terminating at either end. So what's the diameter of a circle? It's any line that goes from one end to the other end going through the center. There's the diameter of a circle. This is also the diameter of a circle. Goes from edge to edge going through the center. Diameter is always equal to how many radiuses? 2 radiuses. This radius plus this radius gives me the diameter. Okay? Semicircle is what you get when you take a diameter, cutting a circle in half. Take the diameter, take half the circle, maybe this half up here, that's what we call a semicircle. A rectal linear figure are any figures we draw only using straight line segments. Okay, so this is a rectal linear figure. This is not. Make sense? And we have special names for certain types of rectal linear figures. If it uses 3 sides, we call it a triangle. If it has 4 sides, we call it a quadrilateral, etc. Okay. Or trilateral, I guess. Of trilateral figures, an equilateral triangle is that which has its 3 sides equal to each other. An isosceles has 2 sides equal to each other, and a scalene, none of the 3 sides equal each other. So 3 types of triangles. If I have a triangle, and the length of this side is equal to the length of that side is equal to the length of that side, we call it equilateral. If I have a triangle, and the length of that side is equal to the length of that side, but this side length is a different length, this is isosceles, and then finally a scalene triangle, something like that. That is different from that is different from that. All 3 different lengths. Good? And then it's a right triangle if that angle right there is a right angle. Don't know, we need the rest of those. Of quadrilateral figures, a square, okay. What's a square? A square is a 4-sided rectilinear figure where all the angles are right angles and all the sides are equal to each other. Now, if this side were equal to that side and this side were equal to that side, then we call it just a rectangle. Okay. Parallel straight lines are straight lines which, beginning in the same plane and produced indefinitely in both directions, do not meet. Okay, what's parallel lines? If I take this line segment, and I take this line segment, and I extend them both directions indefinitely. So I extend that out to infinity, I extend that out to infinity, continuing straight, and that out to infinity, and that out to infinity. If they never intersect each other, if they never cross each other, then we call those 2 lines parallel. Make sense?
Yep.
So parallel, got that. Okay, and that was the last of our definitions. And then for each book, for the proofs he's going to do in that book, he introduces some more definitions before he starts his proofs. So give you a sense of how each book starts, listing out some definitions. Usually after that, there's only like 5 or so definitions introduced in each new book. Okay, so now we get to the postulates. The postulates now are things specific to geometry. We have our definitions about, so that you and I can talk to each other about things, and when I say triangle, you now know what I mean. But now, what can we actually do in geometry? And what can we actually prove? The postulates tell us exactly what we can do. And you're going to notice that his geometry is all about constructions. And so you'll often notice that anytime someone's doing a geometric proof, there's a construction that goes with it. So these are very constructional proofs, and his postulates tell us exactly what we can construct. So postulate 1 says 2 points define a straight line. Or in other words, if I have 2 points, postulate 1 says I can turn them into a line segment, like that. This isn't something we prove. This isn't a definition. I'm not defining something anymore. This isn't something we're proving. I'm telling you it is now a given for geometry. Anytime you have 2 points, you are allowed to connect them with a line segment. This is one of the 5 things you can do in geometry.
Okay.
Actually, when it comes to constructions, there's only 3 of them that are constructions, and then 2 are just saying other geometric properties. So this is one of the 3 things we're allowed to do. Number 2, any straight line can be extended indefinitely. So if I have a straight line, I'm allowed to extend that further. And I can extend this side further if I want. I can extend it as far as I want. That's what the second postulate says. That make sense?
Yeah.
His third postulate says, a point and a line segment define a circle. What does that mean? That means if I've got a line segment here, I put it in our language, it's not quite the way he says it. I've got some line segment here. Now pick one of these points. Let's say A is this point right here. With that point and this line segment, I can now construct the circle centered at A. Make sense?
Yep.
Now, if you'll notice, when people are doing geometry, you're only allowed to use 2 tools. What are the 2 tools you're allowed to use? A straight edge, which is like a ruler, except for no markings. You can't measure in geometry. No measurings, it's just a straight edge, something like this, ignoring the curved part of this. But notice how this allows me to do these 2 postulates. If I have a point and a point, I can use my straight edge now to connect those 2 points with a line segment. So anytime I do that in a construction, on paper, I'm using that postulate. It's the same as a line in a proof, drawing that line segment.
Okay.
What does this one say? Any straight line can be extended indefinitely. So I can line this up with a line segment and draw it further. And if I want to, I can move this down and draw it further. And if I want to, I can move this down and draw it further. And I can extend it down as far as I want. Make sense? Okay. The second tool that they were allowed to use was called a compass. How does a compass work? Got a broken compass here. It works just like this tool right here. Dude, that's bad chalk. There's right pieces of chalk and wrong pieces of chalk. And all the bad chalk needs cleaned out of here. Okay. How does a compass work? Compass is an instrument that looks like this. So remember that we said, no, I got it right. Oh, this one's good. A line segment defines a circle. So here's my line segment, right? What an instrument like this allows you to do is I stick a prong. I have a piece of chalk right here, and then here's just like a needle thing to help me hold it in position. So I take this, I line it up, I put this at one point where I want my center to be. I take my writing utensil, take it out to this point here, and then I twist this around and construct a circle centered at that point. And that's using this postulate. So that's why in geometry you are allowed to use, and only allowed to use, a compass and a straight edge. You're using these 3 postulates every time you use one of those tools. Good?
Yeah.
Okay. So I think we have good understanding for these 3 postulates. Postulate 4 says all right angles are equal to one another. Make sense?
Yep.
And then finally, the last postulate. We're not going to read it this way first. First, I'm going to give you a logically equivalent version, and then we'll read this one, and then we'll stick with the logically equivalent version. What the logically equivalent version says is, given a line and a point not on the line. And when I say a line, I mean now a line in the sense that we use it. So this extends to infinity in both directions. With me so far? So I've got a line and a point not on the line. Euclid's fifth postulate says that there is one and only one line that I can draw through this point such that the 2 lines will never intersect. There's one and only one line. I can't draw another one. If I were to try and draw a line that's slightly tipped from that one, it's going to eventually intersect this line.
Yeah.
So there's one and only one. That's his fifth postulate. And these are the only 5 things in geometry we assume for all the proofs that we do. Outside the common notions, which are consequences of logic, have nothing to do specifically with geometry. So now let's read his and see how it's saying the same thing. If a straight line falling on 2 straight lines, so we got a straight line and a straight line. So if a straight line falling on 2 straight lines, so here's my 2 straight lines, here's my straight line falling on them. With me so far? If a straight line falling on 2 straight lines makes the interior angles on the same side, here's my interior angles, makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side. So he's saying, look at this angle, add them together. If it's less than 2 right angles, or less than 180 degrees, these 2 lines will intersect on that side.
Gotcha.
If it's more, then they'll intersect on this side. And if it's exactly 2 right angles, the 2 lines won't intersect, they're parallel.
Okay.
So a more mouthful way of saying the exact same postulate. The parallel postulate is what's called. But I'll never reference it this way. I'll say, given a line and a point not on the line, there's only one parallel line through that point to the given line. Okay, so those are the 5 postulates. Now we need the 5 axioms or common notions. And these are the things that he gets from Aristotle. Things equal to the same thing are also equal to one another. So if I know that A is equal to B, and I know that B is equal to C, then I know that A is equal to C. This would be a proof of logic, not a proof of geometry. It has nothing to do with geometry. We prove this with logic using identity. Now notice how it makes sense. Things which are equal to the same thing, so notice that A and C are equal to the same thing. Things which are equal to the same thing are also equal to each other. Make sense?
Yep.
Okay? And then if equals are added to equals, then the wholes are equal. So if I know that B is equal to C, then I know that B plus A is equal to C plus A. Equals added to equals are equal. Since B is equal to C, and since A is equal to A, B plus A is equal to C plus A. And we actually proved that one already just using logic, right?
Yep.
And then the next one is if equals are subtracted from equals, the result is equal. So if B is equal to C, then B minus A is equal to C minus A, which has the exact same proof. Good? Okay, 4th one, little weird. Things which coincide with one another equal one another. So if I draw the triangle ABC, so here's my triangle ABC, and then I draw the triangle DEF, so here's my point D, and I draw it up, here's my point E, and then I draw it down, here's my point F. If my triangles perfectly coincide, my triangles are equal to each other.
Okay.
Okay, things which coincide with one another equal one another. Good?
Yep.
And then finally, the whole is greater than the part. Now notice those have nothing to do with geometry. Well, this one kind of does. I guess this one kind of does, but for Euclid they don't. Those are common notions which are used everywhere, not just geometry. Okay, so now we completely have our foundations to start developing geometry. We have our 5 postulates, we have our 5 axioms. Now we're going to see if those are true, what else is true? So we're only going to assume those 10 things are true, the 5 postulates and the 5 axioms. That's the only thing we assume is true.
Okay.
And in fact, using Euclid's thinking, he wouldn't say, we assume these are true. He says, we know these are true from logic. We're going to assume just the 5 postulates are true and see what else is true. So we're going to take our 5 postulates, assume that they're true, apply logic to it, and see what we conclude. And all of geometry is now a logical implication of those 5 postulates, because these come from logic. Make sense? So
Yeah.
that's what we're going to start demonstrating. So start showing you some of these. We'll just read it and then I'll shut this so I can write right here. Don't have to worry about moving the camera. So the first one says that given a line segment, an equilateral triangle exists with side lengths equal to that line segment. Okay? So call this line segment AB. And maybe write, what are we proving right here? Given line segment AB, comma, there exists a triangle ABC. Notice that it uses AB as part of the triangle. There exists a triangle ABC such that triangle ABC is equilateral. So a line segment existing implies an equilateral triangle of that same length exists. And that's what we're going to prove using his postulates. You with me?
Yeah.
All right. AB defines a circle at A. So using AB, let me shift this over a little for my writing. Here's my line segment AB. Now using postulate, which postulate was it? Postulate 3. This is using postulate 3. I know that a point and a line segment defines a circle. So I know since I have this point and line segment, let me move these letters here so I don't accidentally intersect them. I can create a circle centered at A with this as its radius. You with me?
Yeah.
So using postulate 3, I can then construct a circle centered at A with this as its radius. Postulate 3 says, given a point and a line segment, you can define a circle. We just did that. Any questions so far? Let's make sure we fully understand it to begin with, because don't want to lose you later. 2. BA defines a circle. At B, again we're using postulate 3. So postulate 3 tells me at B I can construct a circle using this as my radius. So I can construct this other circle. And my picture is going to lie a lot, but hopefully you can follow the logic anyways. Good so far?
Yeah.
Now typically we reference a circle by its center point. So if I say, look at circle A, that's talking about the circle centered at A, or look at circle B, talking about the circle centered at B. All right? So 3, let C be the intersection, doesn't matter which one, we'll just pick the top one, of the two circles, circles A and circle B. So just mark this point C. You with me?
Mm-hmm.
Now we can construct two line segments using postulate 1.
Yeah.
Then, this is simple for there exists, and we have to write it raw, so sorry, you're going to have to bite the bullet now. Then, there exists segments, line segments I should have said, AC and BC. And this is using postulate 1. So using postulate 1, since we have 2 points, we can take our straight edge and connect those 2 points with a line segment. Since I have 2 points, I can connect those 2 points with a line segment. You with me so far?
Yeah.
Now, 5. By definition, whatever the definition of our circle was, I'll just say definition of circle. By definition of circle, I know that CB is congruent to AB because they're both the radius of circle B.
Yep.
That make sense? So by definition of circle, segment CB is congruent to meaning the same length as, is congruent to AB. And let's do both of them in one go. And notice also that CA is congruent to AB, because they're both radiuses of circle A. So CB is congruent to AB, and I also know that AC is congruent to AB. You with me? Now we use
Axiom 1.
Axiom 2 equals added to equals, oh, no, Axiom 1, he's right.
Yeah.
Things equal to the same things are also equal to each other. Since CB is congruent to AB, and since AC is congruent to AB, then CB is congruent to AC. So since this is the same big as this, and this is the same big as this, then this is the same big as this. So these are all the same length. So one tick, one tick, one tick, saying that they're all the same length. So by axiom 1, comma, we had CB is congruent to AC. Therefore, triangle ABC is, just too simple for it, is equilateral by definition of equilateral triangle. Okay. Period at the end, and then you put a box at the end of each proof to say that you're done. So there's our first proof. So we just really showed that Euclid's postulates imply that any time you have a line segment, you also have an equilateral triangle using that line segment. You see that? Okay, let's do his next theorem.
Okay.
So his next theorem says that if you have a line segment, so here's our line segment AB. Maybe I won't write out all the words this time, I'll just talk through it. Do you guys want to see it right now, or are you good with just talking?
I would like to see it.
All right, we'll write out another one. So if you have a line segment and some random point not on the line segment, call it C, then his postulates imply that you can construct a line segment starting at C in some direction, doesn't matter which, but you can construct some line segment starting at C with this same length, but the same length as this thing.
Okay.
You follow that? So, what are we proving? Proof. Given our line AB and C not on AB, I don't know if it matters if it's on it or not, but we'll just say not on it, and C not on AB, comma, there exists some point D such that CD is congruent to AB. There's some point I can find such that it gives me a line segment, D, such that when I draw that line segment, it has the same length as this thing. That's what we're trying to prove. Everyone feel like they understand what we're trying to prove?
Yeah.
Okay. Now, it's pretty nice proving Euclid's postulates because as a general rule, you're going to have to use the previous postulate to prove your next postulate. Or the previous theorem to prove your next theorem. So the previous theorem says we need told us how to create an equilateral triangle. chances are we're going to need to create an equilateral triangle to prove this.
Okay.
Okay? So, 1. By, let's see, I know I can connect these two with a line segment, right?
Mm-hmm.
So, by, which postulate was that? Postulate 1? By postulate 1, comma, CA exists. Good with that so far?
Yeah.
2. By, I'll call it a theorem instead of a proposition, but, so by theorem 1, the first thing we ever proved, triangle, I already made reference to what D is going to be here, so I need to skip over D. So, triangle CAE exists such that triangle CAE is an equilateral triangle. So in other words, I know from my previous term that it's possible for me to come and construct now an equilateral triangle right here. This isn't necessarily straight. Here, let me change my drawing a little bit so that we don't accidentally get confused by that. So draw that off. Let's pretend to start out like that. So you don't think we are doing something that we can't do. So I start out with segment AB and point C. I connected A and C using postulate 1, and then using what we just proved, I know that I can also construct an equilateral triangle right here. No point re-going through the construction, you already know how to do that. So now, what do we call this point? E. I have point E there, and I know that this side is equal to that side is equal to that side. You with me? Okay. 3. By postulate 2, comma, EA can be extended. Indefinitely. So we'll take EA, we'll only extend it in one direction. We can extend it in both, I just don't want to make my picture messy. So I'm going to take EA and I'm going to extend it, and we'll just do it as a dotted line because it won't be too important here in a sec. So I take this line and I'm extending it out that way. You with me?
Yep.
Okay. 4. By postulate 3, AB gives me a circle. So I'm going to create a circle centered at A with B as with AB as its radius. You follow me?
Mm-hmm.
Okay. So by postulate 3, AB defines a circle at A. Now I'm not going to draw the whole circle because we don't care about the whole circle. All we're going to care about is where the circle intersects this line.
Okay.
So, and I'm going to name this point, what letter are we at? F?
F.
F. So 5, let F be where circle A intersects the line EA when extended. We didn't really name it. So we extend that line. Wherever this intersects that line, we're going to call that point F. You with me so far? Maybe I will draw this as a solid line since I'm being so conservative in how much of the actual picture I draw. Just don't want to make a mess. Okay, so now this is a radius of circle A. Remember, circle A goes all the way around. I'm just drawing a little piece of it so we don't make a mess of the picture. Everyone follow that?
Yeah.
Okay, so this is a radius of circle A, and this is a radius of circle A. So we know that those are equal to each other.
Okay.
Okay, now 6. Oh, no, that's not how I want to do that. Okay. Next, I'm going to extend, let's see, C was our initial point, so I'm trying to draw the line segment C. Okay, So next, I'm going to extend EC indefinitely using postulate 2. And then I'm going to create a circle centered at E using EF as its radius.
Oh, I see. Okay.
Okay? So I'm using EF as its radius, so this is now a different circle, not the same as this one. And I'm going to bring that circle around and draw it, and it's going to come over here and intersect somewhere up here, right? That was terrible. Let me try to guess where I should end, and maybe that will help me draw it a little better. So should be something like, oh well, good enough. You know what I'm saying.
Yeah.
Okay. So then we're going to call this point here D, and then we'll notice that this line segment is the same big as this line segment.
Yep.
So take that one line at a time. So 6, extend, we'll extend it afterwards. Let's first draw our circle, then we'll extend it. So first I'm going to draw my circle centered at E with radius EF. So I'm going to draw that arc of my circle first. So by, what proposition is that? Or postulate?
2.
By postulate, I think that one's 3, the circle one. By postulate 3, EF defines a circle at E, centered at E.
Don't you want to extend the line EC?
Well, now I'm going to extend it.
No, I see.
So 7 by postulate 2,
Yeah.
extend EC extend EC, comma, and let D be the point where it intersects circle E. So now we mark this point off D. So remember, it was this circle arched out there, right? Okay, finally, we put those 2 tick marks there, a little bit prematurely, but I think you see the logic of it. I know that EF, I'm not going to finish writing with words. I know that EF is equal to, or congruent to, I know EF is congruent to CD, and that's by the definition of a circle, right? This is a radius of circle E, this is a radius of circle E, so those are equal to each other. I already know that EA equals EC, because those are both sides of an equilateral triangle. So then I know CD is congruent to AF.
You wrote CD on the top when it's really ED.
Oh, thank you. This one was an ED. Good catch. Yeah, they both need to start with E. EF and ED are equal. Finally, I know that EA and EC are equal. Therefore, CD and AF are equal. And that is by axiom 3. Equals subtracted from equals are equal. This is equal to this. This is equal to this. Thus, when we subtract off the smaller part from each of the bigger parts, the remainders are equal.
Gotcha.
So this is by axiom 3. So I know that this is congruent to this. And we're done. We now constructed a line segment at C with length equal to the given segment. Oh, AB. This was our given segment.
Okay.
You follow that? So now what this enables us to do is kind of like pick up our compass. Notice that the compass I was using, when I pick it up and move it, it stays the same size. It doesn't change sizes on me. That's basically what this postulate allows us to do. I can take a line segment now, which has some length. I can go mark my compass out to that length, and then I can go to some other point and still preserve that length.
Gotcha. So
now using a compass like this isn't illegal. When they use a compass, they just had a string, and they'd hold it at a point and just attach it to a string and move it. And it's hard to preserve how much of the string when you pick it up and move it. But so using a compass like this now isn't illegal after you prove the second postulate. It allows you to continue with the constructions. Or the second theorem, thank you. I may accidentally say postulate because they're called propositions and my wires are crossed. Which is why I should just say theorem. Okay, so that was the second one. You want to see more of these?
Yeah, let's see another one.
You want to see another one? Okay, let's open this up and see what our next one is. Proposition 3. Cut off from the greater of two. Oh, this one's super easy, using what we just had. So not all of them are this complex. That's one of his more complex ones in the first book. But the next one says, given a line segment and a smaller line segment, cut off from this line segment a portion equal to that line segment.
You do that through your theorem too.
And we can do that basically for free from the previous theorem. Ton of chalk in here. I don't know why I've been fighting so hard with these dinky pieces. All right. So from our previous theorem, I know that I can come here. Oh my God. There goes that. It's the right chalk. I wonder why it's drawing so weird. All right. Anyways, so from our previous theorem, I know that I can come to this point and that I can construct a line segment this long at this point, right?
Yeah.
In some direction. We don't get to choose the direction. I can't just pick to draw in this direction. I need to draw it in some arbitrary direction. So I'll draw it out like that, in a way that's not useful for our proof. With me? So now I know that this is the same thing as this, and that's using theorem 2. And now I can use this line segment to define a circle, see where that circle intersects here, and now this is the same thing as that, is the same thing as that. Using his axiom that says equals that equals or equals, I know this is equal to that.
Okay.
And we did it. Here was our initial line segment. We cut off from this line segment a portion equal to some given line segment. Look how terrible that is. Okay. You want to see more of these?
Yeah, let's see another one.
We want to see another one. I could just read it. You guys don't need to actually see it on screen, I guess. If two triangles have two sides equal, so this is proving side angle side. Okay. Side angle side is a congruence theorem for triangles in general. So what does it say? It says if I have two triangles, that's just terrible. Feels like the right chalk. We just get that stick. That feels good. That's 15 apiece, huh? Okay. So I'm trying to draw these two triangles the same. So don't let the fact that my picture is lying to you lie to you. Okay. So if we have two triangles, and I know that this side length is the same as that side length, I know that this angle is the same as this angle, and I know that this side length is the same as this side length, then I know that these triangles are congruent.
Okay.
They're the same size. That's what we're proving. And that's called side angle side theorem, because if the side angle side are the same for two triangles, then the two triangles are the same. So how does this construction work? Well, we need to name this. That's A, that's B, that's C, that's D, that's E, that's F. And we're going to use his fact that if two things coincide, they're equal to each other.
Are you saying that this only works when the angle's in between two sides?
Yes, it has to be a side, angle, side.
In that order.
The angle has to be between the two given sides. So we are not saying this, for example. Just draw a counterexample. Sorry. If I know that this side is the same as this side, and that this side is the same as this side, and that this angle is the same as this angle, I do not know that these two triangles are congruent using this theorem. We're only proving it for the case where the angle lies between the two sides that we know are equal.
Okay.
Then the triangles are congruent. Make sense?
Yeah.
Okay, so just that case. So how do we prove this one? So first thing we do is we're going to pick up this line segment, and we're going to come line it up with this line segment in such a way that B coincides with E. So I'm picking this up, and I'm placing it so that B is smackly on E, and I'm making this line segment line up with this line segment.
Okay.
You with me? Now, since this length is the same as this length, that means C is going to land exactly on F. Good?
Yeah.
Furthermore, since this angle is the same as this angle, then this line segment right here is going to line up exactly on this line segment right here.
Okay.
And then since this and this are the same length, that means A is going to land exactly on D. So if I pick it up and move it, we have C here, that there, and so the two triangles coincide with each other, therefore they're congruent to each other.
Okay.
Make sense?
Yeah.
That's how that one works. You want more of these? Or move on to the next point?
We can move on.
Doesn't just have to be Peter. And if you want to see more, we can continue with more. Okay, we'll move on then to something you might notice in Euclid geometry. Notice that we're always dealing with geometric figures and constructing things with geometry over and over again for everything that we prove. How much of your math was done that way? Almost none. You did algebra. Why on earth are the Greeks doing everything geometrically and nothing algebraically? So even when the Greeks do their algebra, they do it like this. And I'm going to show you two simple things of what the Greeks might do to talk about algebraic quantities and show you a little bit of algebra. So imagine that you, for example, should we show you how to construct a square really quick? We'll do the construction of a square really quick because we're going to be talking about squares and rectangles. So really quick, let's prove that you can construct a square. You with me so far? So given a line segment of some length, some number you might be interested in, we'll call it the length of it A now. How do you construct a square? Okay, first thing I do is I draw a circle centered at here, with this as my radius, and it comes around and marks off a point over here. Well, first I extend this line segment this way. And then I draw a circle centered at here, so it comes around and marks off here. So now the distance from here to here is also A. You with me?
Mm-hmm.
Yeah.
Good? All right. Now that we have those 2 points, all we know is that these 2 points are equidistant from this point. Good? I now draw a circle centered at this point with some length, say out to here. With some length out to here, that's going to draw a circle up like that, right? Using that same radius, I come and draw a circle over here now. We know that we can pick up our compass and move it. So I have my compass right here, I shift it over to right here, and I draw a circle like that. And those 2 points intersect there. Okay, with me? So what I know is that this point is the same distance from there, this point's the same distance from there. So that gives me that we just created this isosceles triangle where this side is equal to this side. You with me?
Yeah.
And I already knew that both these side lengths were A, so that was equal to that. And then if I draw this line down right here, this line's obviously equal to itself. So these triangles are equal to each other. So this right here is a right angle, and this is a right angle. You with me?
Mm-hmm.
Now what do? I extend this line segment up, mark off a portion A, construct a right angle that way, and then mark off and come back down. So repeating that process. Make sense?
Yeah.
Let's see that one more time. I now have my right angle, right? So now I can draw a line up here indefinitely, as far as I want, right? come back to this circle, and create a circle with radius a. That marks off a point up here, a distance a up. So I have a over, right angle, a up, and then I can come right here and do the exact same thing and construct a line segment this way with a right angle, a distance of a to this point, and I can connect those points. And that's an a. And so we constructed the square right here with an area of a times a squared. So that is what the Greeks mean anytime they say a squared. The reason that you say a squared, the reason you read that as a squared, is because that is the way the Greeks represent this is a square whose side lengths are a. They never talked about a squared like this. They talked about a squared like this, where that has side length a.
And they do that with all...
Yeah, furthermore, if you want to talk about x times y, they would represent that with a rectangle. That dimensions x, that dimensions y. And so they're setting it up so that the area of their figures are the same as the numbers you talk about.
So it's very real to them.
It's all done through constructions. So let me show you a really quick construction algebraic proof. One that you guys know real easily, but that we'll do the algebra version and then we'll do the construction version.
Did Euclid introduce like doing the numbers like that, or was that something like the way Pythagoreans have always done it? As far as expressing the numbers through the squares.
So why don't we use numbers the way we do? Let's do the algebra and then we'll come back to the question why they're using algebra this way.
Okay.
Because we do have the answer to that question. Okay. So now let's do a simple algebraic proof. Algebraic proof. When I say a plus b squared, you know that that means that's a plus b times a plus b, right?
Yeah.
Just means it twice. Now you know what, you got to distribute this to the first thing, you got to distribute this to the second thing. We're going to do this super, super slow, one step at a time. So this to the first thing and then distribute that to the second thing. So we have a plus b times the first thing plus a plus b times the second thing. Did I lose any of you in that? Still good?
Yep.
Okay, once again, just change the order on those really quick. So it's a times a plus b times a plus b. Multiplication is commutative. I can change the order I write the terms. I'm just going to write them at first, and I'm going to distribute again. So this is equal to distribute the a to the a, that gives me a squared. Distribute the a to the b, that gives me a times b. Plus distribute the b to the a, that gives me b times a, which is the same thing as a times b. Distribute the b to the b, that gives me b squared. Good? Which is equal to a squared, plus we have an ab here and an ab here, so we have two ab's, plus a b squared. Okay. So we proved a plus b squared is equal to a squared plus 2ab plus b squared. That's doing it with algebra.
Yeah.
How would the Greeks prove this here? Because the Greeks did prove this. They do it all through constructions. So, first off, I need to construct a plus b squared.
So
I need to construct a square whose side lengths are a plus b. So I need to construct my square. Here's my square. And I'll make a the bigger of the numbers. So here's a, here's b, here's a, here's b. Here's a, here's b, here's b, here's a. So notice this whole length right here is the length of a plus the length of b. This whole length right here is the length of a plus the length of b. So the area of my whole square is a plus b squared.
yeah.
Good so far? Now, let's count up the areas. What's the area of this square? A squared. What's the area of this square?
B squared.
B squared. What's the area of this rectangle?
AB.
A times b. What's the area of this rectangle?
AB.
A times b. Now they go through terrible proofs to show We're still cheating a lot by using our algebraic notation. I'm just giving you a sense for it. We're obviously not going to prove this because we didn't work our way all the way up to this. But so now you see that's equal to square of side length A plus 2 rectangles of side length A times side length B plus a square of side length B. And so you show that A squared plus A plus B squared is equal to that whole thing. Good?
Yeah.
So that gives you a taste of how they did their algebra. They developed algebra, they just developed it through constructions. They didn't develop it using the algebraic notation that we know and love. And there's a reason we went to algebraic notation rather than doing it all through constructions, because it's way easier. Constructions are pain.
Can you do anything in algebra through constructions?
No.
Okay.
Algebra goes beyond constructions. So, now the question is, why? Why did they develop their algebra this way? It goes back to, what did they know about the square root of 2? What did the Pythagoreans prove about the square root of 2?
It's not a number.
It's irrational. You cannot represent this as a over b, where a and b are integers. It's an irrational number. Yet, can you construct the square root of 2?
Yeah.
Yeah, that's super easy. Take a square of side length 1. Right? Look at the diagonal. What's this diagonal if we call this x? Well, we know from the Pythagorean theorem, this is a right angle. We know from the Pythagorean theorem, we proved that way earlier in this class. But we know from the Pythagorean theorem that 1 squared plus 1 squared is equal to x squared. This side squared plus this side squared equals this side squared. Right? So, 2 is equal to x squared, or in other words, x is equal to the square root of 2. So we can construct that number real easily, or we can construct that value, we'll say, real easily, but it's irrational, right? And for the Greeks, that's the definition of a number. An integer over an integer is what they mean by a number. So their way of saying this is the square root of 2 isn't a number.
So they just...
And yet we can talk about it through figures. And so figures seem for some reason to be able to talk about more than numbers can. So let's not limit ourselves to proving things with numbers. Let's go beyond that and use figures to prove everything. So this is why they prove everything geometrically. When they do number theory, they prove it geometrically. When they do algebra, they do it geometrically. And when they do geometry, they do it geometrically. Everything they do geometrically, because they thought fundamentally, for some reason, constructions can talk about values real easily that numbers can't. Obviously they were wrong, but that's why.
And it made sense.
Yeah. And so that's why Euclid's Elements is developed all from these 5 postulates. It's amazing. Okay. So I think that gives you a good sense of Euclid's Elements. We can do more postulates if you want. We can be done if you want.
That's Euclid.
Is that all of philosophy?
Yep, that's the end of philosophy. So now we set up a systematic body of knowledge. A body of knowledge where you just take your 5 postulates and you start looking at what they imply.
And it can be more than 5, right?
It can be more than 5, but in geometry it was 5. And so we just had our 5 postulates listed, our 5 first principles, to use the philosophical language. We had our 5 first principles of geometry, and you took postulate 1 and postulate 3 together, and that gave you theorem 1. And then when you took theorem 1 along with postulate 2 and postulate 3, that gave you theorem 2. It may become some other theorem down here. This theorem uses that, and it uses this, and it uses this. Those together imply that theorem. And you start building out this whole web of hundreds of theorems, all implied by just these 5 postulates.
Yeah.
And so every field of knowledge now tries to do this. If you do special relativity, Einstein's special relativity, he has 2 postulates.
What are they?
The first one is basically Galileo's theory of relativity. It says, I'll tell you, but you won't know what I'm saying. The laws of physics, it basically says the laws of physics are the same for everyone. Okay, that's, technically I'm lying a little bit, but that's basically what it says. 1, the laws of physics are the same for everyone. 2, the speed of light is a constant, is a law of physics. So it's the same for everyone. The speed of light is the same for everyone. Those are his only 2 postulates for special relativity. Now he also uses, he presupposes math, but those are the only 2 physics postulates that he introduces. for classical mechanics, we use Newton's three laws. Newton's three laws. An object at rest remains at rest unless acted upon by force, or an object in motion remains in motion unless acted upon by force. All forces is equal to mass times acceleration. And then finally, for every action, there's an equal and opposite reaction. Those are like the three postulates of classical mechanics. So every systematic body of knowledge comes back to its basic postulates. And so they all tried to model on this, and we still do. We still follow this exact same model. We just are more precise in our language now. We have better abstractions for talking about things. But ultimately, it's following the exact same pattern. We're basically doing exactly what Euclid did in his Elements. And we'll notice what Euclid does in his Elements is what pretty much any rigorous textbook does.
Is that why we went so rigorously into the organon?
Yes.
Okay.
That's the foundation of scientific bodies of knowledge. They all follow this pattern now. Everyone was trying to reproduce in their separate fields what Euclid did with geometry. It became the standard. And so that was the whole point in studying geometry. Used to be, education's broken now, the point in studying geometry used to be to understand this, what a systematic body of knowledge is. That you start out with some fundamental assumptions and you just determine all their logical implications. And the point was to train someone, train a student, to be able to do these things and determine the logical implications of some given set of assumptions. And it keeps being dumbed down to, well, what are the real world applications of that geometric theorem? Oh, I can't find anywhere in the real world where given a line segment and a point, I need to put a line segment on that point. So why are we teaching kids how to do that? What a waste. They completely miss the point. So, yeah.
Did you use Euclid to teach geometry when you did your class?
No, I used something better and worse.
Okay.
Better in terms of rigor, I used a word called Gilbert's Axioms. And he's way, way more precise than Euclid. Euclid is fast and loose. Now, Euclid's really good compared to everyone else, but compared to modern math, modern rigorous math, he's playing way fast and loose. For example, in our first proof, we drew two circles, and then we said, so we had our line segment from the center of one circle to the center of the other circle, right? Mm-hmm. And we drew circles here when we were creating our equilateral triangle. And we said, look at the point where they intersect. How did you know those circles intersected?
Guess that
You're playing fast and loose. It's obvious from my picture. So, no, I did a rigorous one from what are called Gilbert's Axioms. So he was the one who finally went and improved upon Euclid properly and rigorously listed everything out. And so his geometry is just as good as it gets.
So why is it worse?
It's worse because since it's so rigorous, it's more abstract and it's harder for a typical student to grasp. Since Euclid's geometry is 100% based on constructions, you can see every proof. There's a visualization that goes with it. When you're proving with Gilbert's axioms, no construction required. It's just a proof. Never need a picture. So Greeks designed their whole geometry around constructions. And so it's a very visual thing. And so you can see it. You can see exactly what's happening. Now you can't do constructions where you're going through Gilbert's axioms. And you can't show constructions and see what's going on. But it's a lot more rigorous. So it's much, much better for people who are already real comfortable with mathematics, but it might be worse for people who are new to mathematics. And Euclid's Elements might be better.
So it's kind of like topology?
Yes, in terms of rigor. But it's not as abstract as topology. That one's really abstract. But yeah. So that's the beauty of the work. It's a wonderful book. Should have offered this up as something we could just continue with. Just going through Euclid's Elements.
That sounds like fun.
Yeah, I think next time I do a geometry course, I will just go through his elements rather than doing it with Gilbert's axioms, depending on who my students are. I wish last time I did geometry, I would have just used Euclid's Elements, because it would have been better for the students I had.
Makes sense.
But I wanted to go through using Gilbert's axioms, because I never did that.
Well, if we got the same people, then that would be fun.
So, yeah. Any other questions? All right, so we'll call it there. That ends philosophy, working up to systematic bodies of knowledge. Now that you know your philosophy, you can start your math. So we'll start algebra next week.